With us, and the floor is yours to talk about advanced concept for adsorption-based gas vapor separation purification with different degree of complexity, and of course the topic which is very important, the air capture as case studies. The floor is yours,
Thank you so
Professor
much.
Youssef.
Thank you so much, Dr. Ainawi. It's my great pleasure to be with you today and share with the community some of the research that's been doing and at the concept stage on separation and purifications. So thank you so much for inviting me for this conference on sustainable energy systems. You will see that everything is about energy. Everything what we do is about energy. If we develop, when it comes to materials and development of materials for specific process, everything is about energy. As a chemical engineer, as a process engineer by background, I'm coming from oil and gas. And in my career, I was more interested in the purification and separation side, more on the environmental side. This was my topic of my thesis on looking at purification and separation processes. So let's start with some very important numbers about separation and purification and transformation systems in industry. That's actually, that people don't know this much. That actually in 2024, it represents just purification and separation only, not transformation. That actually represents 15% of worldwide energy consumption. It's actually represent also almost 5 gigatons of annual carbon dioxide emissions. In order to purify our commodities, we have to spend a lot of energy. Now, if you add transformation to it, which is catalysis, that's almost close to 35% of worldwide energy consumed in transformations, separation, and purifications. Give you one number. If we use in our days, we use in our usual every day, we use plastic, for example, for different purpose. Plastic, the origin is ethylene and polyethylene and propylene. It's coming from ethylene and propylene, and this is only this olefin separation from paraffins. That's actually 1% of worldwide energy consumption. It's huge. So that's the reason why, and if we continue the business as usual, population is growing, we need more commodities, it will just be a disaster if we continue using the actual technology. So that's the reason why there is a need to make advanced or more cost-efficient processes, meaning, and the processes mean it's a lot of aspects of engineering, but one of the most important is the heart, and the heart is the materials, the sorbent, the catalysts, the membranes, and so on. Just to give you some perspective, if we go from, for example, from a distillation and this, which is actually the most used separation technologies in industry, if we go from distillation to adsorption or membranes, that actually represents 75% to 80% of reduction in energy. And I'm giving some example here with some complex separations, ethylene, as I mentioned, propane, propylene, butane, isobutane, and all those are commodities that we use and we don't see them. They are in your fridge, they are in our daily use. Now let me talk a little bit about, to enter my topic today, is to talk about the complexities of separation and purification. We'll not talk about transformations, not about catalysis today, but more on separation and purification. So there is different type of complexities that we work on. So there is a complexity related to the scale and the conditions. I'll give you example here about supplying energy from or producing electricity from natural gas or from oil or from coal. If we just take 500 megawatt power plant energy, that actually could power a city of around 4 million people, maybe Casablanca or half of Casablanca, maybe to Marrakesh. That's actually present 5 to 10 tons, and I will give more details about that later on. 5 to 10 tons CO2 per minute, which is actually huge. This is one of the complexity. The other complexity that we can have is the minimal differences between molecules and shapes. Minimal difference in shapes, minimal difference in size. And I'll give here example of natural gas that has methane, a lot of impurities like CO2 and H2S. And they all have basically molecules with more or less same size and same shape. The other main complexity is the minimal difference in chemical physical properties. And here I mentioned already the case for example, here of ethylene and ethylene. In this case here, where you have actually, there is almost same physical chemical property. And in this case, we use distillation, and it's huge towers, distillation towers with a lot of trays, and that's make the separation extremely energy intensive. So this coming back to the case of the 500 megaton that actually can power a city of around 4 million. That's actually present 10 tons, 10,000 tons day of CO2. And if we apply everything, all the clean combustion, advanced gasification technologies, we still have almost 5,000 to 7,000 tons a day, which is represent 3 to 5 ton a minute. Which is extreme. This is actually what we see, okay, in what we have. This is an example of a big pilot in Saskatchewan, where we have it says actually 115 megawatts power plant, which is approximately enough to power 100,000 Saskatchewan homes. Very important information from this slide is actually the conversion technology that's used right now, that we use mainly for natural gas, but actually now the community or the industrial community trying to implement in flue gas in power plant is amine scrubbing. This is actually very energy intensive in terms of OpEx, and it has a lot of problems of corrosion that actually increase the capex aspects. Give you here some numbers that we will use is that ICOSES for recycling of this ICOSES you need around 100 kilojoule per mole of CO2. Just remember this number. This is extremely important number that I will use later on for comparison purposes. CCUS it's actually or CCS is a complex multidisciplinary problem. This is basically for environmental perspective. Carbon capture can be used, can be captured from in stationary industrial applications for transportations. Okay, but there is one option which is air capture, meaning that we absorb CO2 from air around 400 ppm. That give us some flexibility in terms of the location of the capture, and also from the composition, all the bad things in flue gas, for example, like NOx, SOx get diluted in air. So all the aspects of adsorbent cyclability is removed because those NOx and SOx are very harmful to the materials, whether they are adsorbent or membranes. So from CO2 was a lot of people have been talking about CO2 in the last maybe 20 years, but CO2 separation was existing in more than 100 years now in technologies. There was a lot of applications for energy, for health and safety. For example, here a lot of we use a lot air. For example, air air in our daily use, for example, and this air or nitrogen or oxygen that's used in hospitals, or nitrogen, for example, now we think about using nitrogen for green ammonia. We use actually air separation, and the current technology is distillation, cryogenic distillation, and before doing this, we need to remove CO2 from air. So there's already technologies for that. In natural gas as well. For health and safety, a lot of people don't know that there is anesthesia machine, there is a system, chemical-based, that actually scrub CO2 from air. That is actually for patients, military applications and space applications. There's also a lot of systems existing for a long time ago. Okay, so one of the systems that is used right now for being used with NASA is based on lithium hydroxide. It's actually canisters that are actually used in space shuttles. So that actually change our perspective about CO2 capture. People think always huge scale industrial applications, but there is already existing systems that have been used by NASA or by the Russian Space Agency, which is actually kind of canisters that actually this is actually one of the limitations why right now NASA and the Russians space agency they cannot go to Mars because this is actually represent a weight, and if we want to go long distances we need more weight, and this is they cannot afford for the launch of the rockets. And so one of the first attempts to address the problem, whether for air capture or for CO2 capture from flue gas or natural gas, is to use basically the amines as a combustion technology and put those amines in porous materials. And why is that important? Because amine scrubbing, the drawback is that you have to mix amine with water, 70% of water in the column. And you know that the energy that you need to spend to heat water is extremely high, and that's the reason why it's energy intensive. The alternative here that I'm showing in this slide is that we put we graft, or we polymerize, or we just put covalent amines in the pores, and then we absorb CO2 by impregnation, for example, or by grafting or polymerization. This system has some drawbacks. I will talk about that later here. And one of the drawbacks is stability that actually been addressed in one of my work in the past at the University of Ottawa. But still, we addressed only CO2 cycling, but we still CO2 degradation with CO2, but still we have a lot of degradation with SO2, degradation with many things. But for air capture case, it's not a problem. Because here we can really absorb a quite amount of CO2, around 4% weight, close to 1 millimole per gram, or 1 mole per kilo. Okay, now as I mentioned in my title, we are looking for, and in my introduction, we are looking for cost-efficient systems for CO2 capture, or for separation in general, or for CO2 capture in particular, and air capture in particular. And as you know, there is always different kind of bond energies. And of course, there is, and the more you go for covalent, for example, covalent interactions, or p-bound interactions, there is actually, or acid-based interaction, they are very high. So we have to reduce. What we need to do is make sure that the interactions that we will have with our sorbents or our membranes or whatever we are doing as separation agents, it should be mild, and we have to be below 60 kilojoule per mole. And this is extremely important. Now that to be in this range, we need to avoid chemical substitution. That was my research objective for the last almost the last 20 years. Looking at systems that can absorb selectivity CO2 at different concentrations, but with physical absorption. And you will see later on. So looking at some papers in 2012, for example, there was a big statement that actually we cannot adsorb CO2 with physical solvents at low concentrations or very dilute systems with CO2. This is a big statement in important journals. That's what I will show that is wrong, and we changed. We changed not by a specific material, but we changed by introducing new concepts. These concepts that I will talk about today. So what we want actually to have move from, this is actually a graph showing the energy required for regeneration or for cycling. This is the very important. And we have the uptake, okay? So what we would like to do, this is actually an interesting paper that I published in Chemical Engineering Journal. You can look at it in 2016. It has a different description about this concept. What we want to do is actually to move from 100 kilojoule per mole for CO2 energy that we need to provide to recycle the CO2 from the solvents to around a range between 35 and 55. And this is actually what allow us to have a very energy friendly system for separation or for CO2 capture, whether from air or from other sources. And in order to do that, actually, when looking at the mechanisms, because when you have different mechanisms of absorption, you have the equilibrium-based, which is based on interactions. You have kinetic-based, and you have full molecular sieving systems. What we are looking for is a combination between equilibrium and kinetics, and I will explain more later on, and to give a combination of both. I will skip this, and this is just an example of a material that was developed by NASA to address the same problem we are trying to address. So it was a SAPO-based amino silica phosphate material, and they could get the energy to around 45 kilojoule per mole. This is basically the same thing that we are doing. So here, to just explain the concept that I want to convey today, we have to always connect. The important is to connect the process properties, the separation agent metrics with the process metrics. So for the process, you need all the most important parameters are recovery, productivity, purity, and commodities, which are basically linked to selectivity, for example, for the purity, recovery, the gas uptake, and in case of productivity here, more which is related to membranes in permeation and flux. So what we want to do is, for example, if we take a system that is composed from a molecule A and molecule B, for example, what we want is we want a system that actually has this combined kinetic and thermodynamics concepts. To be more specific, if I have, for example, a molecule A, which is the blue curves, and a molecule B, which is a red, and I want to have a infinite selectivity for A in favor of B. We need, for example, this is a curve of adsorption items that we need to have, very steep where and the uptake is low, and the kinetics should be also very fast in favor of A and defavorable for B. This is a curve that you always use for my students to explain them. Well, what I want to convey is that you have a favorable curve of kinetics here and thermodynamics, and the molecule A to be highly selective versus B in a physical absorption regime. Physical absorption regime, I repeat again, not chemical. You need to have here a molecule A that's in this place here, and the curve, and molecule B here. Molecule B here. Molecule A is highly favorable kinetically and thermodynamically, and molecule B is highly defavorable thermodynamically and kinetically. So this is basically and this is what we've been looking for in the last maybe 20 years, and we could achieve that? That was actually by looking at one of the systems that is one of this very simplistic topologies in meta-organic frameworks, where actually is just a series of channel-based MOFs, actually, based on piperidine and pyrazine as linkers or molecular building or the organic building blocks. And with the pillared SF6 anions, this was the first discovery. We went from this big. This is actually what you see here, just for audience, is actually a huge magnification, a big magnification of what's really happening inside. But this is really at the angstrom scale that you see, and here is actually the structure of the platform that we wanted to do. So you can have here you have a large pore size of the channel, the channel-based, very simple, one of the simplest topologies in MOFs. And here we have an interpenetrated when we added actually a layer here, and we have a more dense structure, and with the same ligand here, which is piperidine, and by changing the piperidine to pyrazine, and this will give this structure, which is that's very confined, highly dense, and it was actually discovered in if I remember very well, 1994 by Professor Zavorotko. People didn't look at it at all. They just did nitrogen adsorption at 7.7, which is a typical characterization. And it was non-porous back then, and it was put on the shelf. Nobody looked at it. And we took this in 2011 actually by Professor, in collaboration with Professor Zavorotko, and we've been able to discover this concept. So what is this concept is about? It's about actually a system that we have a CO2 that is favorable kinetically and thermodynamically, meaning that the CO2 will take the place in the pores. Favorable kinetic, the first will come to the pores and will absorb in the CO2 will be in high spot, and nitrogen will not find any space to absorb. Still in the physical adsorption regime, which is extremely very important. This publication or this work was published in Nature because of this concept. And what is interesting is that some smart people that actually I met in conferences, they read very well and they understood this paper, and they have been able to apply this concept to other materials, which shows the universality of this concept. They applied on zeolite. They looked at the metrics that we found in this our paper with this platform based on SF6, and they apply it to zeolite and to other MOFs based on oxalates, and it works well. All right, now very important things that I want your attention here. It's extremely important things. So when we talk about CO2 capture, there is so many applications. And difference in these applications is actually the concentrations. Maybe time is over, right? How much time left for me, Dr. Inawi? You are muted, Dr. Inawi.
I think you have some more time. I think you can make.
Very good. Thank you so much, Dr. Inawi. So basically, you have different applications with different CO2 concentrations. And if you go from, for example, biogas, where there is concentration is 50%, you go down to syngas, 30%, flue gas, 15%, up natural gas 5%, and up to air capture. So there is difference. So we can basically classify those technologies by different types. So there is bulk CO2 separation, CO2 purification, and low concentration and trace CO2 removal. So this is basically the how we classify. Those are you need to address them in a different way. So for example, here you have different materials that are used for biogas, and it's actually at the industrial level. Same thing for syngas processing. Flue gas is still in the development, but there is many other possibilities. Natural gas already used. and CO2 removal in confined space and air capture still under development. So if you look at the adsorption isotope or the capacities or the shape of adsorption isotopes, they are like that. The more you go from biogas to air capture, you have a very steep adsorption isotopes. This is actually the main thing that we look when you are adsorption or separation scientist. And what is important here is that for biogas upgrading, you don't need very high selectivity. You need it for air capture. There is systems for biogas where they actually use water, just water for upgrading biogas and reducing CO2 to some levels. So this is the first parameter. Second parameter is CO2 adsorption energetics. The conventional mechanism that's used in amine scrubbing or zeolites or is adsorption by equilibrium, which is energy. So the more you go from biogas to air capture, meaning from 50% to 100 ppm CO2, you need to have high adsorption energetics. But there is two parameters, or there is one parameter that was overlooked and nobody looked at is the uniformity of energetic adsorption sites. How those energy adsorptions are uniform in the pores. This is extremely important. And you can see that the more you increase the CO2 concentration, the more you need to have more and more uniform energy within your adsorption sites in the material, in the porous material. Something that is actually very, very famous, which is surface area. When people look and say, oh, I need the high surface area for my application. Yes, it is important for biogas, not important for air capture. Because air capture, you need to have, it's very diluted and surface area is no more important. All right. So to a little bit give you an idea about when we do adsorption and we do separation work with adsorptive or even with membranes, we always look at heat of adsorption, which is actually the enthalpy of adsorption, which is the energy that we need to provide to recycle adsorbents or recycle membrane, for example, or adsorptive membrane. And what people see generally is that you have this kind of curves. That is actually, there is some uniform adsorption sites, and but it's fade away, and you have almost nothing. It's go down. But what we need to look at is something that like this that is very uniform. This is what it translates the uniformity of adsorption sites, is to have a very constant heat of adsorption, which is here I'm showing in curve C and curve B. Curve A. Curve E is very low. Curve C is what we need to have a system that has good capacities or good performances for CO2 capture from air. Now, if you we can classify this by application. So for air capture, this material B can make we can work with it. It's fine. However, when the more you go in concentrations, the more the material with curve B will not work at all. You need to have only materials with the curve C for enthalpy. The more you go in high concentration, this is extremely important, and you will find it in this paper that we published in 2016 that shows actually this concept.
You have more 5 minutes.
Sure. So thank you so much, Dr. Inawi. So let me basically summarize what I want to say. The SAF6 was the first generation. We moved to second generation that's actually more stable, and with the team back then at KAUST, it was amazing. This paper was published in JACS that shows actually that the material that we develop here, you see there are only 50 or 54 kilojoule, for example, here, and this one, but they have almost the same capacities as amine scrubbing, and this is important. What you see here is actually a real single X-ray measurements, the real position of CO2 in the pores, really. This is actually a real measurement, not just a picture. And yeah, and to leave some time for questions, I will skip this. This is actually another, just to show you the third generation, but it's not related to air capture. It's more related to flue gas. Very important thing is that, as you know, people know a lot of MOFs, took a lot of MOFs. MOFs is very tunable platform materials that we can tune, and this is exactly what one example here is that we changed the pillar of that was in the first material that I showed in Jack's paper with the aluminum F5 pillar, and that allowed actually to introduce a coordinated metal sites, open metal sites, and in this case we were able to absorb CO2 and water at the same time. So, and humidity was not a problem. Here at UM6P, this work is continuing with more advanced materials that actually never been discovered before, with more interesting properties. And currently we have developed this system that is actually very passive, that we don't use any energy, only solar, and this for the operation. Even for the heating, we created the material inside the column where there is surrounded by greenhouse, where actually we can actually use actually difference in temperature between the day and night. As you know, Ben Gurir has a huge difference. It's not like Marrakesh, has a big difference between the night and the day, around 20 degrees. So we are using this as a driving force to create the conditions for heating to recycle the material. It's actually still under development, and we hope to reach this tutorial 5 this year. And with this, key takeaways for me is that for air capture or for CO2 capture in general, we have to move away from chemical absorption to physical absorption, based on physical absorption, and being below 50 or 55 kilojoule per mole. That basically will allow us to have a cost of CO2 capture per ton below $100 a ton. So with this, I'll thank you and thank the organizers for giving this opportunity, and I'm open to for any discussion or any questions. Thank you so much.
Thank you very much.